Do you like zoos? Do you like going to the zoo? Today I will show you a zoo. We'll take a tour. Well, this zoo doesn't have animals in it, but hypergraphs. It's an online zoo, so you can look at it. So if you want to look at the zoo, it's so this is a web page which contains a lot of geometric hypergraphs, and my plan today is to show you my favorite geometric hypergraphs. It's Gabor's top favorite hypergraphs, and we will focus on chromatic number of these hypergraphs. So I will show you examples that are interesting in the sense that they have a large chromatic number. Okay, so what are geometric hypergraphs? Let's start at the beginning. We have a set of points in the plane, and we have some objects. Take your favorite objects. So, for example, some squares, or some circles, discs, or whatever. Take your favorite objects, and how to turn this into a hypergraph? Well, the vertex set is just the points, and each geometric object corresponds to a hyperedge. Okay, so this hypergraph here has, I don't know, 8 vertices and 3 edges. Okay, so this is a very natural way to construct a hypergraph. And of course, we are interested in the combinatorial properties of these hypergraphs. What can we say about them? Let's say we fix something about the objects, like you are only allowed to use, let's say, axis parallel rectangles. That gives you a family of hypergraphs that you can achieve this way. What can we say about the combinatorial properties? Okay, and I will only focus on the chromatic number today. What can we say about the chromatic number of these hypergraphs if I fix my favorite family of objects? And well, of course, so you could say that, okay, this is stupid. There is this hypergraph. I put 1 point and only one of my objects. And this is clearly chromatic number. I don't know if we can even define the chromatic number. So like, if I color this, I will have a monochromatic edge in my hypergraph. So I want to forbid this, of course. So I'm going to look for n uniform hypergraphs. Each edge should contain exactly n points. Okay, because I want to avoid these small counterexamples. Okay. So I will talk about hypergraphs. We heard a lot about graphs, coloring graphs, a lot of results. The thing is that everything gets much more complicated once we start using hypergraphs. Already, the notion of coloring is not very clear. There are a billion ways to generalize colorings to hypergraphs. We will go with the one that James already mentioned. So I will look for a coloring so that in each edge, I have at least 2 colors. So this is not a 2 coloring because I have a monochromatic edge here. That's not good. But this is a 2 coloring of this hypergraph. Each edge contains at least 2 colors. Okay, I don't want all colors to appear in all edges or nothing special. Just I should not have monochromatic edges. Okay. So I have an uniform hypergraph, and I want some large chromatic number. How hard could it be? I just start putting down some edges. If I have enough edges, surely at some point the chromatic number will increase, right? So how many edges do I need? Erdős asked this nice question. So like, let's say, let M and B the minimum size of the edge set of a hypergraph. How to denote it? So it's not too colorable. Okay, so I want an n-uniform hypergraph. I don't say anything about the number of vertices. I just want few edges to enforce that the chromatic number is not 2. And this already shows that it's not going to be easy to construct these hypergraphs because we need a lot of edges. So Erdős, here is a nice theorem. As I promised, there will be some probability in the talk, but I will keep it at bare minimum. So don't get scared. So Erdős proved that so 2 to the n minus 1 is a lower bound for this value. So this is a very easy probabilistic method proof. You just take a random coloring. Okay, if you don't have enough edges, a random coloring will give you a good 2 coloring. I will give you 2 minutes to try to solve this. To wake up a little bit, everybody is sleeping. I can see too much drink yesterday. Okay, so it's just a simple calculation. So if I look at one of the edges, what is the chance of this edge going bad, going monochromatic? Well, there are 2 to the n ways to color this edge, and only 2 of them are bad, if all red or all blue. Okay, so the chance is just 1 over 2 to the n minus 1. Okay, but then I can use the union bound. I have this many edges, and for each, the bad probability is this. So in total, the probability of bad events is less than 1. Less than equal, but clearly it cannot be equal because if I color everything red, that will be in each of these events. So the union bound, it clearly cannot hold with equality here. Okay, so this already shows that it's not going to be easy to construct hypergraphs with large chromatic number because we need a lot of edges. Okay, well, of course, we can say something better than this. So what is the state of the art? So this is 0.7 times the n times square root of n over log n. Okay, not much bigger, but still bigger than the obvious proof. This also uses probability. This one is scary. Okay, so this one is not. And the upper bound is something like n squared times 2 to the n. Also from Erdős. If you don't know who proved the theorem, guess Erdős. It works most of the time. So this is a nice open question. Can you improve on these bounds? Either construct a hypergraph with small number of edges, but it's not too colorable, or prove that any hypergraph on this many edges is too colorable. Okay, so the task is not easy. So the question is, what can we do? We need a lot of edges. What strategy we should pick to create these hypergraphs? And we have, I think, I mean, there are a couple of things we can do. We will look at 3 of them. We can do some algebraic construction. We can do probabilistic arguments. And we can do some combinatorial constructions. Okay, and I will speak a little about each one. So let's start. Yeah, so in general, yeah, one thing that I also wanted to say that if you have a hypergraph and you want to show that it's not colorable, it's usually hard. Okay, because you have to show that no coloring works. If you want to show that something is colorable, it's usually easier. You just have to show one coloring and then you are happy. So these proofs, when you want to prove that something is not colorable, is in general harder than finding a coloring. Okay, so we either go for some structure, like algebraic structure or combinatorial structure, or we do some kind of overkill and we show that we don't even have a chance to get a coloring, even if we do some random things, random construction of hypergraphs that will already work. Okay, so let's start with algebraic. James already told you some of this, so we have van der Waals theorem. James already told you this. What was it? So we have if we have the integers and we color them with some colors, then I don't know. Then we will find. So if I take enough integers and I color them with k colors, then I will find a monochromatic arithmetic progression. Okay, so how is this a hypergraph? Well, of course, when you have any kind of Ramsey type result, you can turn it into a hypergraph. You just have to define the vertices, and so like here, the vertices are the integers, and each arithmetic progression is an edge in the hypergraph. Okay, and then this theorem says that this hypergraph is not k-colorable if I pick the base set to be large enough. Okay. There is a nice generalization of this theorem called this. We have here's Jewett theorem, which is like a high-dimensional generalization of this one. Here, we want to color, instead of the integers, we want to color a large cube. So what do I mean by that? I pick some integer n and some dimension d. I will color these points. So, for example, I don't know. This is here 3 squared. So I look at the high dimensional grid. I want to color this. And so what is the statement? What are the hyper edges here? Well, I want to have these hyper edges and these ones, and also this one. So I will take all collections of size n that form a combinatorial line. What do I mean by a combinatorial line? So what is a combinatorial line? It means that I fix some of the coordinates. So like here I want 2, here I want 2, I don't know, 1 something, and And in certain coordinates, I put a star. And such a sequence corresponds to the combinatorial line where I replace the stars in all possible ways with the same number. So let's say I'm working in this one, two. So if this is in 3 to the 6, then this line corresponds to 1, 1, 2, 1, 1, 3. I have two ones here. 1, 2, 2, 3, 1, 3. Okay, and this collection is the combinatorial line corresponding to this sequence. Okay, so I replaced in each row, I replaced the stars with the same number going from 1 to n. Okay, so for example, this is not a combinatorial line. Okay, this is a geometric line. You would expect it to be in the hypergraph, but we don't need all of these. This is not a combinatorial line. So we take rows, columns, diagonals, but not all of them. Okay, and so Hales-Jewett theorem says that if I fix n and I fix the number of colors, let's say k, then there exists a d which depends on them, such that any k coloring of n to the d, which depends on n and k. So any k coloring of this has a monochromatic combinatorial line. Okay, so here the statement is about the dimension. If I pick the dimension to be high enough, then a monochromatic line will appear. Okay, everything clear so far? Okay, so the proof of this theorem and the proof of Hales van der Waals theorem is it's like an inductive or double inductive proof, and we only have terrible bounds, very terrible ones on these numbers, like how large we should pick these ones, like towers of exponents. So they exist, but we don't have good bounds on them. Okay, so this is a nice algebraic construction. I won't talk about the proof, but let's use it for a geometric hypergraph. How to turn this into a geometric hypergraph? Well, it's not very surprising that I'm going for lines here. What I do, I take this cube and I project it onto the plane. Okay. So I take this high dimensional point set and I do a generic projection. So like I pick a stupid direction. I don't want things to fall onto each other and so on. So what do I get if I project? I get a set of points, and all combinatorial lines will correspond to lines that contain exactly n points. Okay, because I took a generic projection. And now I know that if I k-color this point set, no matter how I do it, I will find a line, a geometric line, which is monochromatic. Okay, is it clear? So if I take points with respect to lines, then the chromatic number of my geometric hypergraph is not bounded. I can achieve any chromatic number that I want. So it's not bounded. Okay. And this, so, okay, now we understand points and lines. We can get the chromatic number as large as we want. This also works for a bunch of other objects, namely anything that can be made very thin in any direction. So for example, you want a geometric hypergraph with rectangles. I do the same construction, and instead of looking at the lines, I just put very thin rectangles here, and they will give the same hypergraph. So again, the chromatic number is as large as I want. Or you say, let's take ellipsoids. Well, I can make the ellipsoids very thin, and again, I get the same hypergraph. Okay, so this works for any objects that are very, very thin, and I can rotate them in any direction. Okay, so what happens? So we need to look for some other objects that don't behave like this. So one of the things you could ask, okay, what if I don't allow rotation? What if I have axis parallel rectangles? Maybe if I don't allow rotation, the chromatic number will become bounded. And it doesn't. So this restriction is not enough. And the proof for this, I think, is very interesting because it's a probabilistic proof. It's from Akhtar, Szegedi, and Chen. They showed that if I take a uniformly random point set from a square of enough points, then this will, with high probability, already have large chromatic number. Okay, so this is not an explicit construction. We construct the hypergraph by taking a random point set, and then we collect each n-tuple into an edge. This gives us a random hypergraph, and they show that the chromatic number is large. And they did the same that James already mentioned yesterday. What you usually do in this case is that you show that the independence number is small. So they actually show that they show something like roughly the, let's say, something like n log n. So they roughly show that the independence number is at most n log n with high probability, and then this means that need roughly log n colors to color this construction. Okay.
What do you mean by any n-tuple and edge? So how do you have to pick these rectangles?
So you need to pick the rectangles, axis parallel rectangles, which contain exactly n points.
Just all of them which contain n points, that's your definition of it.
Yeah.
Okay.
Yeah. So in this case, I make a geometric hypergraph using axis parallel rectangles. I can take any collection that I cut out with the axis parallel rectangle. Okay. And this is a random construction which shows that it works. Okay. So this is a fun application if you want geometric hypergraphs in 3-dimension, let's say. For example, you want a point set so that, okay, so let's do it here. I want a point set in 3-dimension, and I want to look at edges that I can get using a regular simplex. Okay, so I can take hyper edges that I can separate from the rest using a tetrahedron. Okay, so here is something interesting, like, and let's say I allow tetrahedrons of any size. So here's something interesting. If you have a plane, you can place your tetrahedron so so that the intersection of the tetrahedron and the plane is a rectangle. Okay, so I cut it through these 4 points. Okay, this is a rectangle. So I can place this construction on a plane and use tetrahedrons to cut out the axis parallel rectangles by enlarging the tetrahedron or pushing it closer to the plane. Okay, so anytime you have a result on axis parallel rectangles, you can usually use it to get a result on tetrahedrons in like homotets of a fixed tetrahedron in free space. Okay. So, okay, so this was algebraic constructions, probabilistic constructions, and now I will talk about some combinatorial constructions. So the next thing I want to talk about is, okay, the chromatic number is large for lines, for axis parallel rectangles. How about something much nicer? Let's look at unit circles. I have a set of points, and I look at unit circles that contain exactly n of them. What can I say about the chromatic number? Now, immediately the chromatic number drops. Why? We can take the Delanoid triangulation of the point set. Okay. Does everyone know what's a Delanoid triangulation? Okay, so the Delanoid triangulation of a point set is something extremely useful. So if you want to remember one thing from this talk, this is probably the most useful one. If you want to work on point sets, you can define a very nice triangulation. It has a lot of nice properties. The way you define it, you connect any 2 points that can be separated by a circle from the rest of the points. Okay, it doesn't have to be a unit circle, a circle of any size. Okay, so this can be separated. This can be separated. I don't know. Maybe this can be separated. Yeah. So the thing is, this is going to give you a planar graph. Why is it planar? Why is it planar? Well, I have an edge here and another edge here. And basically, both of them can be separated from the rest by a circle. If these 2 circles are disjoint, then of course the edges are also disjoint. If these 2 circles are not disjoint, this line through the intersection point will separate the 2 edges. Okay, so this must be a planar graph. And with some more care, it's not hard to show that it's not just a planar graph, it will really give you a triangulation on the point set. Okay, the triangles that you get, the triangles are exactly the triples that can be separated by a circle from the rest. Okay, so why is this useful for us? Well, it's again, I don't go into the details, not hard to see that if I take this Delanoid triangulation and then I take any circle, then it will contain a connected part of this planar graph. Okay, it's not very surprising. If I have some points here and this is a large circle, I can shrink it and somehow get these edges here. Okay, so any circle will cut out a connected part of this planar graph. Okay, and now I just use the 4-color theorem. Okay, 4-color theorem colors this triangulation here with 4 colors. And then And then I have a 4 coloring for my geometric hypergraph. So if I have a set of points, I take the Dama triangulation, I color it with 4 colors using the 4 color theorem. And then any circle that cuts out exactly n will contain a connected part of the of the graph. But if it's connected, then it contains at least one edge, and that one edge already has 2 colors in it. Okay, so the chromatic number here is at most 4 for any n. So even for small ones. Okay. So okay, but is it 4 or less? And it was a conjecture of Koch that this is actually a shoe too. He wrote a paper, but he didn't publish it, and later turned out that this paper was not correct. So if you never met Koch, I found a photo in my bag. This is how he looks. Very friendly guy. So he conjectured that you can always 2 color your point set, at least for large enough n. I don't know. Okay, so let's say I look at circles that contain thousands of points, then I can always 2 color it such that any such circle will contain 2 of the points. Okay, so this is not the case because so I will show a hypergraph that is not 2 colorable, but we can realize it even with unit circles. How much time do I have? Okay. So here's the hypergraph. Okay, so how is this hypergraph constructed? We're gonna go for something, yeah. So I want to create a hypergraph. Let's start here. I want to create a hypergraph with a nicer property. So I want it to be a hypergraph that is not 2 colorable, but I want something more. So I will create a hypergraph PKL such that it's going to have red edges and blue edges. So I have a partition of the edge set. The red ones are K uniform. The blue ones are L uniform. And instead of not 2 colorable, I want something stronger. I want to say that no matter how I 2 color this, I want to say that either one of the red edges will be completely red, or one of the blue edges will be completely blue. Okay, so if one of the red edges is completely blue, I'm not happy yet. Okay, so you understand the difference? It's something stronger. I will specify which edges should be red and which edges should be blue. Okay. Well, for small k and small l, it's easy to define this hypergraph. You just take one red edge and you put this blue edges here. And now this is, what is this? This is P1K, right? If all red, then I have a red edge, which is K uniform. If at least one is blue, then I have a blue edge, which is 1 uniform. Okay. And now I want to construct PKL from PK minus 1L and PKL minus 1. Okay, so I will take this two smaller constructions, and I want to combine them into a bigger one. And this is how I do it. So here I have P32 in this part. And in this part, I have P23. And so if you forget this and that, here we have 3 vertices in each red edge and 2 vertices in each blue edge. So what I do, I add an extra vertex and I put it into each blue edge. This increases the uniformity of the blue edges by 1. So I will have like a 3 uniform graph here for both red and blue. And I do the same here, but for the red edges. I place this construction and I add this new vertex to all the edges that are red. Okay? So why does this work? If I color this part with 2 colors, either I get a red edge and I'm completely red and I'm done, or I get a blue edge, completely blue, but that forces this to be a red point. And the same happens here. We force this to be the other color, which is not possible. So we will get either a blue edge or a red edge to be completely blue and completely red. Okay. All right. So this is the hypergraph. This is a tricky one that requires 3 colors. And now the only thing we have to do is to realize it with unit circles. Okay, so it's not enough to have the hypergraph. We have to put the geometry in. And okay, forget this part. So how you do it, the construction will always look like this. I will have a lot of blue edges, like a lot of blue unit circles close to each other, and a lot of red unit circles close to each other, and all the points will be in this very small area here. Okay. For PK1 and P or L, or anyway, for these ones, it's easy to create. You just put some points there, and you only need one of the colors, so it's easy to do. And then if you have 2 of these constructions, one here and one here, you can combine them by putting the new point here. This will be inside each of these red edges and each of these blue edges. Okay. And so if you can do this, then it's not hard to argue that you can push these constructions to be very close to each other, so that in the end, the construction again looks like this, that all blue are very close, all red are very close. And then you repeat, and you can build a geometric hypergraph with unit circles that require 3 colors. So the chromatic number is at least 3.
But you can't repeat this forever, can you?
Sorry?
You can't repeat this forever, otherwise the chromatic number would be arbitrarily large.
No, this creates just a non-2 colorable construction. The chromatic number didn't increase the uniformity. I needed the iteration to increase the uniformity. So I want large edges. That's the hard part. Yeah. So you can do it any number of times. Okay. So this shows, and actually the chromatic number is at most 3. So we proved with Demeter Pavlody a couple of years ago that if you fix your favorite convex set in the plane and you look at translates of it, then the geometric hypergraph that you get is going to be 3 colorable if n is large enough. So the uniformity is large enough, which depends on the shape. But for each shape, there is an n such that n uniform geometric hypergraphs with translates of this set have chromatic number at most 3. So in the case of the circle, translates of the circle give you all unit circles. Okay. So how much time left? Not much. No. What else did I want to say? Okay, so I will just very briefly sketch the last part. Okay, this was unit circles, and you can ask, of course, what if I am allowed to use any circles of any size? Okay. Of course, this argument still works. So the chromatic number is still at most 4. And it is conjectured that this is also the conjecture of Paolodi and Kessler that the chromatic number is at most 3, but this is not the case. So we can create n uniform. So for any n, we can create n uniform geometric hypergraphs with chromatic number exactly 4. And this is even trickier than the previous one. Just let's briefly sketch the idea at least for the hypergraph that we want to realize. So we need a new hypergraph. This one doesn't work. So here is a nice little hypergraph. I take a rooted tree. And I use it to define a hypergraph in the following ways. It will have 2 types of edges. I take all descending paths that start at the root and end at the leaf. So all of these will be edges of the hypergraph. Okay, and the second type of edges, for each vertex, I collect the children of the vertex into an edge. Okay, this is my hypergraph. I claim that this is not too colorable. Why? Well, the root is going to have some kind of color, let's say red. And then I want to follow this color down the tree. If there is a child which is red, I can keep going. If I reach a leaf, then I'm good. I found the descending path which is monochromatic. If I get stuck, what does that mean? If I get stuck here, then all the children of this one must be blue. But that's a monochromatic edge. Okay. So this is not too colorable. And actually you can do this in a more general setting. But let's say I have a hypergraph so the chromatic number is at least C here. This is hypergraph 1, and I have a hypergraph 2 with chromatic number at least C minus 1. Then I can do the following trick. I pick one of the edges of this hypergraph and replace it by many edges in such a way that, so like I take a lot of copies of this edge, and in each copy I add the new vertex. Okay, so I split it. This kind of corresponds to what would happen if I would put some new leaves here. The descending hyperedge would split into these new ones, right? And then I also want to add this thing here. Instead of simply adding a single edge here, I can add any hypergraph here that have some nice coloring properties. So in these new vertices, I want to add my H2. So I add H2 here. And I claim that the resulting hypergraph, so this new one, will have chromatic number still at least C. If I color this original hypergraph with this new edges, well, this required C colors. So my only chance is that, so this still has all of its edges except the one that I split. So my only chance to color this part is that these edges that are in the split, no, that are in the split hyper edge, these must have the same color. Okay, but then none of these new vertices can have the same color as these ones. So I cannot use one of the colors on the new vertices. I only have C-1 colors here, but I assume that, okay, my indices might be off by 1 anyway. So, well, the point is that I color this with one less number of colors, then that means that I will get a monochromatic edge here because I assume the chromatic number here. Okay. So why do I explain this more general one? So this is only not two colorable, but if I do this construction, starting with this simple hypergraph, this is not three colorable, and I keep extending the edges of this one using this one. So this is not three colorable, this is not two colorable. As I keep extending, I will get a bigger hypergraph, which is not three colorable. And if I do it carefully, it will be n-uniform, and I can realize this with circles. Okay, I don't have time to go into the details of how to realize this with circles. It's not very simple. But the thing is that this is possible. So this hypergraph construction, so you keep enlarging your hypergraph while maintaining some like some properties about the chromatic number. This works. This can be realized with circles. So the chromatic number 4 in this case. Okay. So to end my talk, I will give you a nice application of this theorem. So probably all of you know that, as we already mentioned it. If I have a planar graph, I can color it with 4 colors. Okay, so that any of these edges will have different colors at the endpoints. Okay, 4-color theorem. Now you might wonder, what can I achieve with 3 colors? Okay, so I only give you 3 colors. Can you do a nice coloring here? For example, can you do a coloring with 3 colors? Let's say now whites, red and blue, so that the monochromatic components, like this one and this one, and this one and this one, can you always do a coloring such that each of these components are small? Okay, very natural question. I cannot color this correctly with 3 colors. Well, maybe 3 colors are enough to, I don't know, say that I will only have groups of at most 10. Okay. Now I'm going to show that this is not the case. With 3 colors, there are planar graphs where no matter how you 3-color it, you will have large monochromatic components. Okay, and there will be nothing new. I will just repeat some of the things that I already said. I take this construction. So I take this point set, which requires 4 colors with respect to circles. I take the Delanoid triangulation of this one, and I repeat what I already said. So let's say you claim that you can color this with 3 colors with small components. Then I say that, okay, wait a minute, because of this theorem, I can find a circle which contains n of the points and all have the same color. And as I said, any circle cuts out the connected component of the Delanoy triangulation. So I found connected part with n vertices, all of the same color. Yeah. We're out of time, so that's it.